Hello there. We're going to do 6.2, angular and linear velocity. But first, a brief review of 6.1. Now, what is a radian? So we're just going to start right there and review this. A radian is where you have a radius that we will call r, and it equals a sector length, s, which equals that radius. So in other words, if I connect this up here, that distance of, say, this yellow strip right here is equal to this radius. That is called a radian. And this angle right here is 57.3 degrees. So I'll make a list of stuff here. 1 radian is 57.3 degrees. Some more stuff here. One rotation, or what we're going to call today, one revolution equals 360 degrees, and it's also equal to 2 pi radians. 2 pi radians, which is equal to 6.28. So 2 pi is the same as 6.28 radians. That went way farther out there than I intended it to, but all of that is so true, and you have to memorize that. We also looked at a couple formulas for the area of a sector and the arc length. All right, and we saw that the arc length equals theta times r, or r theta, either way, and the area of a sector is 1/2 r squared theta. Okay, so I just wanted to review those little basic concepts. Now, today we're going to do something called angular displacement and angular velocity. And I want to explain the difference between angular velocity and linear velocity if I have time. So first of all, if I have a circle, it's like right there, and it has some sort of angle that is spinning around, this thing is spinning around like this, rotating, and I said, okay, if I have 3 revolutions, I'll put REVS for revolutions. In other words, that angle spins around 3 times. And I want to know how many radians is that. So in other words, what would this angle be if it spun around 3 times in radians? Well, to do that, I'll put in radians there. To do that, you just take 3 times the number of radians in 360 degrees, or in a revolution. And we just saw here that it's 2 pi, which is the same as 6.28. So just take this times 6.28. All right, so that is 18.84. 18.84 radians. This theta right here is called the angular displacement. Angular displacement. Lots of new vocabulary here. The angular displacement is how far this angle went around. Well, it went around 18.84 radians. Okay, this would be the answer. So just to make sure everybody's got this, if I said, okay, what about 5 revolutions? Well, you would just take that times 6.28. 5 times 6.28, and that would be 31.4 radians. And that would, of course, remember, be theta. That part's easy. Now, a new formula here, and we'll do bright white so it really sticks out. This Greek letter right there is called omega. The Greek letter omega, right? And that stands for angular velocity. angular velocity. And that equation equals theta over t, where this is time, and it doesn't have to be in seconds. It doesn't have to be in minutes. It can be pretty much in anything, minutes, seconds, hours. And this is the theta that we just solved for. This is called the angular displacement. Okay, the angular displacement. Now, angular velocity is how fast this side right here, everybody see that? It's how fast this side is moving. Okay? So, for example, if you were on a carousel going in a circle, and you were on the inside horse and one of your friends was over here on the outside horse, well, the line connecting you, if you took a can of spray paint and spray painted a line that went right through here, you guys would still be on the line every time you spun, right? Even here, you would still be here, and down here, you would still be here. You would have what's called the same angular velocity, but your linear velocity would be completely different. In other words, if you guys were tracing out little circles as you went around on the interior horse versus the exterior horse, well, you could see who's going in the same period of time farther. So since you're going farther over the same period of time, you're going faster. So if you're on the outside, you're going faster. The best way to do this, of course, is to go outside and have somebody stand here, hold hands out to another person, hold hands out to another person, and another person, and then start rotating. This person out here is at a dead sprint, trying to keep up with this person who's barely moving, to keep this in a line here. You can see that. So that is the difference between angular and linear velocity. Now, I want to do a problem right here. All right, so this problem, this is number 19. It says, find the angular velocity in 1.8 revolutions, that's REVS, 1.8 revolutions in 9 seconds. So if this thing spun almost 2 times around in 9 seconds, what would its angular velocity be? Well, you got to remember that a velocity is just a distance over time, just like in physics class. But according to this formula here, this omega is equal to the angular displacement over time. Well, we need to do this yellow stuff here to this green problem first. So we're going to take 1.8 revolutions and multiply it by 6.28 to figure out its radian measurement. So let's see here. 1.8 times 6.28 is 11.304, and that would be radians. Radians. You got to keep these units straight. And now, according to the formula, omega W, that's the worst omega ever. Let me do that again. It's like a W with a loop in it, equals this theta over time. Well, this is my theta here. So I'm going to say 11.304 radians divided by the time period, which is 9 seconds. All right, and we'll just divide that number. Just keep it on your calculator. Divided by 9 is, and now you can round it. So angular velocity is 1.3 radians per second. And that is the unit for angular velocity. All right, you guys have a good one.